Okay, so you've done it. The code is written, the game actually runs, but the journey isn't over, not by a long shot. Today, we're talking about that final, absolutely crucial step, making the leap from just being a coder to becoming a real engineer. Someone who can not only build something, but can actually prove that it works.
Seriously, you've put in the hours, you've fought with all those pesky bugs, and now your Hangman game is alive and kicking. It runs from start to finish. That's a huge deal, and you should be proud of that. It's the perfect foundation for what's coming next.
But here's the real kicker, the question that separates the pros from the amateurs. It's not just about getting it to work once, on your machine when the wind is blowing in the right direction. Can you actually defend it? Can you prove its logic? Can you show that it's rock solid?
And this slide, this really gets to the heart of what we're talking about. Look, a coder, they make something work, and that's great. But an engineer proves it works, under pressure, with weird inputs, every single time. And adopting that engineering mindset, well, that's what this whole final phase is all about. So, how do you even begin to build a project you can defend? Well, it starts way before you write a single line of Python. It all begins with the blueprint, the professional planning and documentation that maps out your entire system before you even start. First up, we have the data flow diagram, or DFD. The best way to think about this is like the high-level architectural plan for your game's data. We're not getting bogged down in the weeds with loops or if statements here. Nope. All we care about right now is mapping the movement of data. Where does it come from? Where does it go? And to draw these diagrams, we use a formal language, a set of standard symbols. Now, these are the official NSA standards, and using them correctly, that shows you know what you're doing. So for example, a circle is a process, like check, guess. A rectangle is an external entity, that's the player. That weird three-sided box, that's a data store, like your word list file. And of course, the labeled arrows show the data itself, like player_guess, flowing between all these different parts. Okay, so if the DFD is our big picture map, we're going to need a legend to understand all the details on it, right? That's exactly what the data dictionary is. It's the single source of truth, the ultimate guide to every single variable your program is going to use. And here's a perfect example, taken right from your own project. Let's say another developer, or your examiner, looks at your code. They see a variable called score. They check the data dictionary and boom, it tells them everything they need to know. It's an integer, it tracks the player score, and it has to be a valid integer. See? That level of detail is what makes a project professional and easy for others to understand. All right, so we've mapped our data. Now we can finally zoom in on the logic itself with a flowchart. This is where we get into the nitty-gritty. Remember how the DFD was all about data movement? Well, the flowchart shows how decisions are actually made. It's the if-else statements, the loops. It's basically the beating heart of your game's logic, all laid out visually. So, with that solid blueprint in place, the path forward is crystal clear. We're not just hacking away at the keyboard anymore, hoping for the best. We are translating a professional plan into a working program. It's time to build. And this is where your plans smash into reality, using the core tools you know in Python. You're using lists or arrays to hold your word bank and the letters the player has guessed. You're using if-else selection to figure out if a guess is correct. You're using a while loop for repetition, which creates the main game loop that keeps everything going. And you're using functions to organize it all into neat, logical blocks. See? Every single part of your blueprint has a matching tool in your code. Okay, so the game is built, it works when you play it normally. But is it robust? What happens if the user types in their name instead of a letter? Can it handle someone who is actively trying to break it? This is the question that leads us straight into the world of quality assurance. Yeah, I like to call this next phase the gauntlet. Your job here isn't just to check if your code works, it's to intentionally try to break it. Why would you do that? It's simple, because finding the weaknesses yourself is the only way you're going to build a program that's truly strong and reliable. Now hold on, we're not looking for simple syntax errors here, the kind that just crash the program. We're hunting for something much, much sneakier, the logic error. This is when the code runs just fine, no crashes, no smoke, but it produces the wrong result. Like the score not going down when it's supposed to. These are the bugs that require some real engineering detective work to find. So how do you find these sneaky logic errors? You need a real strategy. You have to test with what we call boundary values, checking the absolute limits of your system. Like, what happens on the player's very last guess when the score is exactly 0? And you have to test with faulty data.
What happens if the user enters a number, or a special character, or just hits enter? A truly robust program handles all of these weird cases gracefully instead of just falling over. And when you do find a bug, you don't just start randomly changing code and hoping for the best. No, you follow a professional workflow. First, you identify the weird behavior. Then, you set a breakpoint in VS Code right where you think the problem is. Then, you step through the code, one line at a time, watching the variables as you go. This lets you see the exact moment your logic goes off the rails. In all of this, the careful planning, the solid build, the tough testing, it's all been leading up to this one final moment, the defense. It's about proving you own your work, that you understand it inside and out in the final exam. All right, let's get down to brass tacks. Mark your calendars. Friday, the 27th of March, period 1. This 30-minute exam is, frankly, the anti-plagiarism filter. It's where you prove you're not just a coder who copied something, but a real engineer who can explain and defend their own solution. And look at how this exam is broken down. It's super revealing. Notice how little of it is about just having working code. 10 marks are for explaining your logic. Another 10 are for your debugging skills on a new piece of code. And 5 marks are just for being honest about your process, including how you used AI to help you learn. This exam is 100% about your understanding. Okay, so here is your action plan for success. It's simple. First, practice the walkthrough. Seriously, grab a friend, a family member, anyone, and explain your code out loud. That's how you practice for those 10 marks. Second, break your own code on purpose. Get comfortable with that VS Code debugger. And third, finalize that logbook. This isn't just paperwork. It's the hard evidence of your entire engineering process. You know, in the end, it all comes back to this one idea. Anyone can make something that works once. That's the first step. But being able to prove how and why it works, especially when you're being challenged on it, that's the mark of a true software developer. So this is it, the final challenge. You've got the tools, you've got the knowledge, and you've definitely put in the work. The only question left is, are you ready to defend your code?